Hey everyone, I'm Alex, and I'll be presenting joint work with my advisor, Vinod, on correlation-intractable hash functions via shift hiding. So first of all, what are correlation-intractable hash functions? So correlation-intractability is a cryptographic security property trying to capture the hardness of finding input-output correlations of some sort in a hash function. So formally, given a 2T area relation R, so a relation R on T inputs and T outputs, we say that a hash family H is correlation intractable for R if for every efficiently computable adversary, the adversary only has a negligible chance of, given a hash function H, finding T inputs x1 through xt, such that these T inputs, along with their corresponding T hash outputs, satisfy R. So it's plausible for a hash function to satisfy this security property, provided that the relation R is sufficiently sparse, which roughly speaking means that there aren't too many points in the relation. Besides this, this is the only real constraint. Otherwise, it's plausible the hash function satisfies this property, and indeed a random function would. So ideally, we'd like to build correlation-intractable hash functions for as wide a class of relations as possible. Unfortunately, already when they were introduced by Kennedy, Goldreich, and Halevi, they showed that there is no single hash family H that is correlation-intractable for all sparse relations R. In particular, if R is allowed to be inefficient, and if the number of inputs T that you care about is an unbounded polynomial function of the input length n. So in that level of generality, we know that we cannot build a correlation-intractable hash family, but essentially anything less general than that is plausible and on the table. And so the question for this work and many other works is, which kinds of correlation-intractability can we build, and how is it done? So before getting into that, though, let me just talk a little bit about why we care about what correlation intractability is useful for. So already in the single input setting, so t equals 1, they're already incredibly useful because they give standard model instantiations of the Fiat-Shamir heuristic. So that is, there's been this cool line of work over the last few years that has built correlation-intractable hash functions and then used them to build various kinds of non-interactive proof and argument systems that we didn't know how to build before. So it's been very fun working on this line of work, and correlation intractability is very essential here. So that's the main application of correlation intractability that has happened so far. But I want to talk specifically about the multi-input case because although it's quite unstudied, there hasn't been much work done on it. There have already been a few scenarios that have come up where multi-input correlation intractability has seemed quite important. So the first example that people came up with was the setting of trying to set up a common random string when you have many mutually distrusting parties. So you could have many parties, they want to agree on a common random string, but they don't trust each other to produce a truly random string. So what you can do is have each party send their own random string and publish it, and then use the hash function to generate an actual common random string given these many inputs. So that's one plausible use case for multi-input correlation intractability. Additionally, it's quite related to the security of complicated multi-step protocols, especially when there are many parties involved. So it turns out that you need a form of multi-input correlation intractability to hold to have any hope of the Bitcoin protocol being secure. So this is not a sufficient condition, but it is a necessary condition. So that motivates thinking about it for sure. Also, there was this recent work that actually just used multi-input correlation intractability to provably build a different honest majority multi-party computation protocol. So it turns out to be useful for honest majority MPC. And finally, it was also shown how to use multi-input correlation intractability in order to build an error-correcting code, which is computational, where the error correction property is only computational. That is, it's only computationally difficult rather than impossible to violate the error correction property. The trade-off, or on the plus side, what this work is able to do is they are able to build a code with a decoding radius which is larger than what's information theoretically possible. So that's pretty cool. So multi-input correlation intractability seems to be pretty broadly applicable as well, although we're still in the process of understanding what it is good for. But for this talk, I just want to focus on the question of building the tool rather than using the tool. So how do we build correlation intractable hash functions? So let me talk about what was previously known before this work. So in order to do so, we need to narrow our scope quite a bit. So we're going to, for the moment, focus on the single input case, so t equals 1. And we're also going to further narrow our scope from an arbitrary relation R to functions f. So in that setting, correlation intractability for a function f means that it's hard to find a single input x such that hash of x is equal to some pre-specified function f of x. So we've simplified the property quite a bit, but this is still a very non-trivial object and suffices for many of the Fiat-Shamir applications on the previous slide. And so this object we knew how to build. It was known that under standard cryptographic assumptions, you could build hash function families that are CI for efficiently computable functions, or there's a quantifier issue, so it's for any fixed time bound, you can build a hash family that is CI for functions that take that much time to compute. So this was known, and just like a word on how it was accomplished, the idea was to think of the description of a hash function as being an encrypted function. And in the security proof, you would think of the encrypted function as the function being encrypted as being the function that you're trying to avoid in the security property. And the hash family was constructed so that hash of x would output an encryption of a message which guaranteed that the string would not match f of x, that the ciphertext string would not match f of x. So in the original construction, we did this by assuming that we had a fully homomorphic encryption scheme that satisfied a circular security property. That is, it had satisfied some security property where the message you were encrypting was related to the secret key of the encryption scheme. So it was nice, but it had a slightly stronger security property than we wanted. And this was later improved by Pikert and Sheehan to remove the circular security assumption and just rely on plain learning with errors. They did this by carefully instantiating special purpose variants, like a homomorphic encryption scheme with some special, a bit hard to describe properties that removed the need for the circular security assumption. So this is very clever, but the conceptual simplicity was lost a bit in this
construction.
So that was for the single input case, and then in the multi-input case, much less is known. In a joint work with Justin Holmgren, we constructed various kinds of multi-input correlation intractable hash families, but we required very strong computational assumptions in order to build them, stronger than standard, and we'd like to rely on standard assumptions. And then there is just one other thing to mention, which is that because correlation intractability is so general, there are going to be some special cases that we knew how to handle before. In particular, if you just think about relations that only touch the outputs, so relations that just check some properties of the collection of t outputs, then as special cases, you recover some old security properties like collision resistance that we certainly knew how to build. And then Mark Zandri has a work which generalizes this to just all output-only relations. So this is what we knew how to build previously. It's quite a limited class of multi-input relations that we knew, and from standard assumptions anyway. So now let me talk about what we do in this work. So like in a nutshell, what we do is we give a new framework for building correlation intractable hash functions. We no longer use this homomorphic encryption approach. We instead turn to another like primitive from cryptography called shift-hiding shiftable functions, which is related to constrained pseudorandom functions. So that's the area that we're jumping to instead. And we show that they can be used as well to build correlation intractable hash functions. So what do we get out of it? So first of all, we get a different construction of single input correlation intractability from lattice assumptions. This is just recovering the top line result of prior work, but I think the construction and proofs are very clean, and I think it's nice to know. But in terms of new results, we build various kinds of multi-input correlation intractability. First, a class of constructions from lattice assumptions again, and then a broader class of constructions from making use of indistinguishability obfuscation plus additional standard assumptions. So yeah, these are the new things that we built. Let me give a little more details about what these new constructions are. So let me define a class of relations that we're able to capture, which we called shifted linear relations. So a relation R on T inputs and T outputs is an F shifted linear relation if it's checking that the following kind of linear relation holds between the inputs and outputs. So it's checking whether the sum of the outputs is equal to the sum of f of the inputs, the sum of f of xi. So yeah, it's just checking it's checking a linear function on the collection of outputs and the collection of f of the inputs. Yeah, so this is some class of relations. If t equals 1, this just recovers just functions in the single input case, but it's a broader class of relations in the many input case. So one thing that we're able to do is that under the LWE assumption plus another lattice assumption, which also basically follows from LWE, we build hash functions that are correlation intractable for this class of relations. And we get something a bit stronger than this, actually. You can consider versions of these kinds of relations where you're allowed to take weighted linear combinations rather than just taking a sum. So these are the kinds of relations that we can handle just from LWE. And then here's the class that we're able to handle making additional use of obfuscation. So we just generalize basically from linear to nonlinear. So a relation is a shifted relation where it's shifted by a function f, and the base relation is some output-only relation R sub out. If the relation R is just the collection of xi's and yi's, where these shifted outputs yi minus f of xi satisfy the output relation R sub out. So just as an example, you can take R sub out to be like the collision resistance relation, and then you basically get, and that's an example of something already from the previous slide. It's some linear function on these yi's minus f of xi's. That's just an example, but in general, you can let R sub out be an arbitrary sparse output relation, and you'll get something interesting here. And assuming I/O and some mild additional assumptions, then we can build correlation intractable hash functions for all of these relations. And I also want to mention that this also, our technique here, implies new results even in the single input setting. So we can build correlation intractable hash functions in the single input setting just based on I/O plus one-way permutations, which is mostly just a theoretical separation because I/O and one-way permutations don't imply any form of two-input correlation intractability. So it's like a separation between single input and two-input correlation intractability. And also, because of this recent work of Jane, Lin, and Sahai, this also gives an approach for building correlation intractability that does not rely on the learning with errors problem. because you can instantiate the one-way permutations using discrete log. Okay, so these are our new results, our like concrete new results. So now let me just explain how we get them. So the main tool, which I already mentioned, is this object called shift-hiding shiftable functions, which is a special kind of pseudorandom function. So a function family, capital F, indexed by a secret key sk, is shift-hiding if it satisfies some kind of programmability property. So the property is that there's this algorithm shift, which takes the initial secret key for the PRF and takes a function f and outputs some shifted key, case of f, such that the following two properties hold. First of all, if you evaluate the pseudorandom function using the shifted key case of f, you should get the original PRF evaluation of x shifted by f of x. So in the actual construction, this property will also be computational. So it will just be hard to find an x such that this is not true. But you can just think of it as just as being always true for convenience. So this is the shift correctness property. And then second, the family should be shift hiding, which means that the shifted key case of f should not tell you anything about what f is. So in the security game, you're just given a key, and the property says that for any two functions f and g, case of f and case of g are computationally indistinguishable. So this is the object. It's as I said, it's a pseudorandom function family with some sort of programmability property. And so it was known, in fact, before any correlation-intractable hash functions were really constructed, that shift-hiding shiftable functions exist under the LWE assumption, plus this one-dimensional cis assumption as well. Yeah, so this was known, and we end up showing in this work that this this pseudorandom function family, which already existed, turns out to also solve the correlation-intractability problem essentially for free. Let's talk about how that works. So essentially, here's the key lemma for the whole paper, and the lemma is also like extremely easy to prove. So consider the following construction. Like start with some pseudorandom function family, or we're going to assume it's shift hiding. So assume you have a family like this. Then we're going to define a hash family H, where like a hash key is just a shifted key from the SHSF, where the key has been shifted on like a trivial zero function. So it hasn't really been shifted at all, but it is a shifted key. So then hashing an input is just applying the PRF using the trivial shifted key. So that's the hash function, sort of like the only thing you could write down. And then the claim is that if the family is shift hiding, and if it satisfies a one-wayness property, namely it's hard to invert zero, it's hard to invert this function on the output 0. If these two assumptions are true, then the hash family is correlation intractable for all efficiently computable functions. So it's very nice. It just says that with this one additional assumption that you get correlation intractability. So here's the proof. So in other words, what's going on here is that shift hiding shiftable functions give you a correlation intractability self-reduction. It says that to get correlation intractability for all f, it suffices just to handle the case f equals 0, the trivial case, which corresponds basically to the function family being a one-way function. So that's what this is saying. But there is a caveat here, which is that you need the shift hiding shiftable function itself to be one way, and the way this is phrased is that we want it to be one way given the secret key in the clear. So this is a very interesting question. It's come up before, what happens when you give out the secret key for a PRF. Like, can you argue that it's a one-way function? This has been analyzed in the case of GGM specifically a few years ago. But in general, it's a pretty open question, like when this is possible. But we're able to show it holds for particular pseudorandom function families that we built. Okay, but anyway, let me explain the proof of this lemma. It's like 3 lines. Here it is. Suppose that the adversary violates the correlation intractability property, which means that it finds an input x with some non-negligible probability, such that hash of x is equal to f of x for some pre-specified f. And remember that hash of x is just a PRF evaluation of x on this trivial shifted key. So that's what we assume. Then we just invoke the 2 properties of the shift-hiding shiftable function. So first of all, by the shift-hiding property, we should be able to replace the trivial shifted key with the key shifted at f, case of f. And this change should be undetectable. So that means that when the adversary is given case of f, it still finds an input such that hash of x equals f of x. But now this hash of x is equal to the f-shifted evaluation. But we know that the f-shifted evaluation is just equal to the actual PRF evaluation plus f of x. So just plugging that into the equation, we immediately see that this means that the PRF evaluation of x is equal to 0. We also assumed that it's hard to invert 0, so this is a contradiction. And that's it. It's like a very syntactic proof, and it says that you get correlation intractability for all f at the end. So I think this is very nice. So this is the proof of the key lemma, and so the rest of the paper is about thinking about just building the object that was assumed in this lemma. So this is just for the single input case. So like what you also need to do is formulate and prove the multi-input version of this lemma, which is something we do, but I'm not going to cover in this talk. But it's very similar to this lemma. So that's the reduction. So now all we need to do is find shift-hiding shiftable functions that are also one-way functions, essentially. So I'll just explain one of the constructions. I'll explain the LWE-based construction. And there we just show that the original shift-hiding shiftable function based on LWE was already one-way. And so this SHSF that already existed solved the correlation intractability problem. So in fact, what we end up showing in order to get the results for multi-input correlation intractability is that we show that it's actually a collision-resistant hash function, and more generally just solves satisfies this property called sum resistance, which just says that it's computationally hard to find distinct inputs x1 through xt such that any pre-specified weighted linear combination of the hash values is equal to 0. Sorry, the slide has a mistake. The right-hand side of the equation should just be 0. So it's hard to find t inputs whose weighted, such that the weighted linear combination of the hash outputs is equal to 0. Then by the self-reduction, we get this more general property where the f, with an allowed f dependence in the equation. Okay, so that's what we want to show about the LWE-based LWE-based SHSF. And so I'll just sketch the proof that it's one way, or that it's hard to invert 0. And so I'm throwing a bunch of details under the rug here, but roughly speaking, this is what the function looks like. The function that we want to show is one way. The input is x, and the key to the function is specified by 2 random vectors, s and u, along with a collection of many random matrices, which is just represented by this A. A is a collection of matrices. Then the function output is a rounded version of a vector matrix product. So there's the vector SG plus U, which you should just think of as a random vector. and then G inverse of A sub x, so this is a bit decomposition. G inverse of A sub x is a binary matrix. So it's one matrix with binary inputs, so binary entries. And I'm skipping over a bunch of details, but A sub x is some matrix generated using this gadget homomorphism methodology. Okay, so it's a random vector times a matrix with small entries. So we want to show that it's hard to invert 0. It's hard to invert this function at 0. So let's see why. So suppose that we found x such that f of x equals 0. Like taking out the rounding operation, what this means is that this vector matrix product is a short vector. And so we're going to use this to violate some computational assumptions. So to do this, there are two cases. If this matrix A sub x is non-zero, then we have solved a short integer solution problem where the problem is specified by this random vector sg plus u. So sg plus u specifies a problem of finding a vector whose inner product with this vector is very small. And so this is a one-dimensional cis problem, which turns out to be hard. And so if A sub x is non-zero, then inverting f means that we've solved this kind of cis problem. So that can't happen. So the other case is that A sub x equals 0. And in this case, we show that you solve a different cis problem, where the instance to the cis problem is now specified by this collection of matrices A. And A sub x equals 0 turns out to be something you can phrase as a solution to a cis problem as well. So this one is a bit trickier, and I won't get into the details here. But it turns out that you can show this would violate a different cis assumption. So this is the high-level idea of how the proof goes. So that's all I wanted to say. So now just let me conclude. So as I said before, what this paper is doing is it's giving a new framework for building correlation-intractable hash functions, where the main tool for building the hash functions are these shift-hiding shiftable functions. And so we show that shift-hiding gives you a self-reduction for correlation-intractability, which reduces correlation-intractability in hard cases, quote-unquote, to correlation-intractability in easier cases. And this gives a methodology for building them in various settings. So as a result, we make some progress, but on the following two questions, can we build correlation-intractable hash functions from weaker or at least incomparable computational assumptions to what was known before? And the other question is, which relations is correlation-intractability instantiable for in any under any assumption? So these are the goals that we had in mind, and I think that this is a neat new approach for maybe resolving these questions or making progress on these questions. But I think that there's a lot left to be done in the area, and these two questions are still quite far from being solved. So I think hopefully these techniques lead to further progress in the future. And then, so specifically, one really nice goal for the future would be to actually build forms of multi-input correlation-intractability that actually connects to either the applications that I described at the beginning of the talk, or to new applications for specific cryptographic primitives or protocols beyond correlation-intractability itself. So that's everything. Thanks for listening.